Hey guys, thanks for watching. I'm just making this video to help some of you understand better how to solve problems using recursion. If you find it easy to solve problems using recursion, then this video is probably not for you. So the first thing that I want to talk to you about is something called mathematical induction. Now some of you probably already know what this is, but for the rest of you, I'll just explain a little bit about it. I won't show you how to do it, I'll just tell you the ideas that you need to make what I'm about to say understandable. So, mathematical induction is a way of proving that a particular property holds for all of the numbers. It doesn't have to be numbers, but usually it is numbers. And the way it works is that you pick a base case. Usually it's 1. It can be higher in some specific circumstances, but usually it's 1. And after you've shown that the property holds for the number 1, you then show that if the property holds for a particular number, then it also holds for the next number. And I'll just demonstrate how that kind of unfolds. So we've proven the base case that the property holds for the number 1. We've also shown that if it holds for a certain number, it holds for the next number. And that means that because it holds for 1, it also holds for 2. And we can use that property again, that if it is true for a certain number, it's also true for the next number. So because we know that it's true for 2, we can also say that it's true for 3. And because it's true for 3, we can also say that it's true for 4, etc, etc. So this will just keep building upon itself. And there is no number, no natural number that isn't reached by this technique. And it's relatively simple when you think about the fact that you can prove a property holds for every natural number, an infinite number of numbers. The fact that you only really need to prove 2 things, something about a base case and then something about the implication from one number to the next, it's really quite strong. And you can use a similar approach when you're trying to solve problems using recursion. So the first thing that I want to say is that not all problems using recursion can be solved this way. The approach that I'm about to tell you about works when you're working with recursive data types. So these first 2 data types here are recursive data types, and we know that they're recursive data types because here we have the name of the data type, and the name of the data type also appears in the definition. And it's the same thing here. We have the name of the data type, and the name also appears in the definition. For custom data types that aren't recursive, such as this, I know that the name appears here, but this is just the constructor, so we can replace that with a cons, and it will work the same way. So because the data type as a whole doesn't actually appear in the definition of that data type, the technique I'm about to talk to you about won't actually work in this case. Okay, so these first 3 functions are probably functions that you understand quite well. Maybe you done it a few weeks ago. But I'll just show you how you can apply this sort of thinking using the concept of mathematical induction. So when we were trying to figure out the length of the list, we've got to cover the base case first. Always cover the base case, otherwise you will end up in an infinite loop. So the length of an empty list is 0. Okay, we've got that covered. So now we move on to the next case. when the list is not empty. And it doesn't matter what data type you're using. This step will be similar in all cases where you pattern match against a particular part of the definition that includes recursion. So let's just say that there was another possible type of tree A, and it was let's just call it next, and next contains an element, but it doesn't contain any additional trees. We couldn't use this wouldn't apply to situations like this. We would need to define this as well as a separate base case. So we need to define all of the base cases, and the base cases are cases that don't have a recursive definition in them. Okay, but in the case of lists, we've covered the case that doesn't have a recursive definition, and now we need to cover the case that does. And when we cover the case that includes a reference to itself, we can assume that the function already returns the correct result for this part of the pattern. So we're pattern matching against this type of input, where we've got the head of the list and the tail of the list. And because the tail of the list is defined as simply exactly the same data type, we can assume that the function works for that part of the input. So if we assume that the function works for that part of the input, we can call a function on that part of the input, and then we just need to figure out what to do with the part that's left over. So in the case of lists, the part that's left over is just the head. And if you've got a function that will return the correct result when applied to the tail of the list, you just need to figure out what to do with the head. So in this case, we've got the function returning an integer, which represents the length of the tail of the list. And just to deal with the head of the list, we just need to add 1. Because the whole input isn't the tail of the list, it's the tail of the list and the head of the list. So we've got the function, we just assume that it works for the tail of the list, and then we deal with what we need to do to make sure that we also include the head. We can't just assume it works for the tail and then forget about the head, because that won't provide the correct output. And if you're not providing the correct output, then the whole thing sort of collapses. So you do need to deal with the head, but once you've dealt with the head, you can assume the function already works for the tail. This is very similar. It's probably not too much more difficult. We deal with the base case, which is the empty list. The sum of an empty list is going to be just 0. And now we deal with the pattern which is recursively defined. So we assume that the function already works for the tail, and if it already works for the tail, it will return a type that is a number. So we have this part of the function, this part of the expression, which represents the sum of every element in the tail of the list. And we just assume that that works. And after we've gotten that number, all we need to do to take care of the head is just to add the head to whatever number that is. And then this function will work. Reverse list. Now, So the first two examples, you might be more able to easily come up with these function definitions without this approach, but thinking about how to recursively reverse a list just using your working memory, trying to step through a few cases, a few examples, it can be very confusing. It can be hard to do properly because you've got a lot of different things that you need to keep track of in your mind, and this actually simplifies it a lot. And hopefully, after I talk through this example with you, you'll start to appreciate how this can be useful. So we take care of the base case. The base case is the empty list. So the reverse of an empty list is just the empty list. Now, in this case, we assume that the function already works the tail. So if we do assume that the function already works for the tail, then what we'll have is, we look at the type signature, it's going to return a list of type A, and that list will be in reverse. So we have already the reverse of the tail of the list, and we just need to figure out where to put the head. And if the tail of the list is reversed, all we need to do is put the head at the end, and that will make the entire list reversed. And we know that it's of type list of A, which is why we're using the concatenation operator here rather than the colon constructor. And this really makes things a lot easier, and it gives you a lot less demand on your working memory, because you don't need to kind of say, okay, well, if I take the first element and then I put it to the end, what am I going to do with the rest of the list, and what happens when I call a function on the rest of the list? Well, what does it need to do with the first element? You don't need to go through that whole thought process. You can just assume that it works for the tail, and then deal with what you need to do with the head. Now, I also wanted to give you an example talking about trees, because I didn't want my only examples to be of lists. Because if I just showed you lists, then you might find it hard to figure out how to apply this same approach to other recursive data types. And we know that the tree is a recursive data type because its definition includes the name that we've given it. Okay, so we take care of the base case. The depth of a tree, which is just a leaf, is 0. Now we take care of the other case. And the other pattern that we can match against is when the tree consists of a node with an element and 2 subtrees. Now, because these subtrees are types of the same type that you're actually defining, that's where you can use the assumption that the function will return the correct value. So we check the depth of the left child and we check the depth of the right child. Now the depth, because the depth of a tree is the longest path, all we need to do is take the maximum between those two depths. So if the depth of the right tree is 4 and the depth of the left tree is 100, we're not going to say that the depth of the overall tree is 4. We're going to say that, and we're not going to say it's 104 either. We're going to say that it's 100. Okay? And because we're assuming already that the function will return the correct result, we just need to figure out the max between those two numbers. And all we need to do then is to deal with the fact that this result is actually the correct result for the children nodes. It's not the correct result for the current node. So if we have the maximum of the two children node depths, all we need to do is add 1 to that number, and that will give us the depth of the current node, or the tree that the current node is the root of. And because the return type is an int, we know that this will return an int representing the depth of the left child, and this will return an int representing the depth of the right child. So these will be 2 ints, and we can take the maximum of those, which will give us the depth of the longest child, whichever it will be, and to incorporate the current node into that result, we can just add 1 to it. And I hope that makes some sense. This concept of when you've got a recursively defined data type, deal with each of the cases, but when you see that a particular part of one of the cases is a reference to the type that's being defined, so in this case we'll have this. So in the definition of tree, we have 2 cases. We can have as many cases as we like, but in this particular definition we have 2. We've got to deal with each case. So we've dealt with the leaf, and then we deal with this case. But because these 2 parts of this case are references to the type that's being defined, that's the situation that we can just assume that it works. Okay. So, and I hope you understand it, and I hope you can see how it can be very useful in solving problems. Because once you're assuming that the function works for a decent amount of your actual input, solving that additional step, which is just this part and then this part, becomes so much easier. So if that doesn't make any sense at all, or it made a little bit of sense but you need a bit more information, or you have any questions, feel free to email me or post on Piazza. But for now, I hope you've learned something. I hope this has been beneficial, and thanks again for watching.